Hi, everyone. Thank you for joining us for today's webinar. My name is Sakshi Sethi, and I manage the OSA membership program here at OSA. I'm really excited to introduce today's presentation. It's by two of our members, VPIphotonics and Infinera. So I'd like to introduce today's moderator, Chris Maloney. He's a Director of Business Development at VPIphotonics. And I'm going to go ahead and turn things over to Chris to get us started. Thanks.
Yeah, thank you, Sakshi, and thank you everybody for joining us today. I'd like to just introduce a few of our speakers before we get started. Today we have Dr. Gloria Huffler, Director of Advanced Development at Infinera, Eugene Sokolov, Senior Photonics Applications Engineer at VPIphotonics, and Dr. Yuchun Zhao, PIC Development Engineer at Infinera. And today the topic that we'll be speaking on is about paving the way for indium phosphide photonic integrated circuits from concept to tape out. And so here's just a brief overview of the agenda today. We'll talk about what motivated our partnership, give a discussion on Infinera's indium phosphide PIC foundry, and then have an overview of the VPI toolkit PDK for Infinera, and actually have a live demo of that, of the circuit and system level simulation. And then lastly, we'll discuss, okay, once you've done your design, you can export a netlist, and then what's the workflow now at the Infinera foundry. So I'll just start off with our partnership motivation. I'd like to first discuss some of the applications and trends in photonic integrated circuits in general. And so I think most of you are probably familiar with the PIC applications. So some of the typical ones are optical communications, medical sensors, and automotive. Today we'll actually be focusing our example on optical communications, as the datacom market is one of the dominant segments in terms of photonic integrated circuits. Now this is what we'll be focusing on, but I want to just remind you that all of the concepts that you learn about today, those can also be applied to the other applications mentioned here. And so this datacom market is really being driven by internet traffic. And with the coronavirus pandemic, that internet traffic is only increasing. And so this demand is really pushing the industry to develop new standards for 800G and 1.6 terabyte. And so how do we actually get there? And so one of the most obvious answers is, okay, well, just increase the switching speed. And there are some limitations with the electronics in regards to that. So other methods are used in conjunction, such as parallelization. So things like fiber, wavelength, or spatial division multiplexing, but also advanced modulation formats. So with non-return to zero, you have two amplitude levels, so you're transmitting 1 bit per sample. With pulsed amplitude modulation, we actually can have multiple amplitude levels and transmit more than 1 bit per sample. And actually the example that we will work through a little bit today has to do with coherent modulation, and specifically quadrature amplitude modulation, which involves transmitting multiple amplitude levels and phases, so that we can transmit 4 or more bits per sample. So that's an introduction to the example that we'll go through today, specifically in an IQ modulator. So one of the main EPDA challenges in supporting the PIC ecosystem, as outlined by the Integrated Photonic Systems Roadmap, is that we need to improve the maturity of the foundry PDKs. And this actually requires an orchestrated effort between foundries like Infinera and software vendors like VPIphotonics. So foundries should be implementing more of their design, process, and test information into PDKs, which is exactly what we've done here. And at the same time, be working with the software vendors where we can improve our tools and flows to support design for manufacturing and improve yield and cost. So we like to think of our collaboration between Infinera and VPIphotonics as in phase. So we're constructively interfering with one another. And the way that we do that is that both of our companies are domain experts in optical communications. So Infinera is very vertically integrated with systems and networks. And this domain has been VPIphotonics, our bread and butter, if you will, for over 20 years. And one of the most important things that makes this partnership work really well is our focus at the circuit and the system level. And this enables fast and simple simulations for PIC designers. So if you're a designer, you don't necessarily need to know the device physics behind each and every component. And this is actually where VPIphotonics, this is what differentiates us from some of the other vendors, where we're looking at things from a top-down point of view, where our expertise is really at the system and the circuit level, and some others really focus more at the device level. And last but not least, this is very important as well, is that the PDK building blocks are actually based on characterization data and test measurements instead of only simulation data. So now that you have some background on what motivated our partnership, I'd like to turn things over to Dr. Gloria Hoffler, and she will discuss a little bit more about the Infinera indium phosphide PIC foundry and discuss how you can get involved there. So with that, I'll stop sharing my screen and turn things over to Gloria.
Thank you, Chris, for that kind introduction. Let me now give you a little bit of background first on Infinera, and then describe our PIC capability. All right, there you go. So we are Infinera, a US-based optical network communications company. We're founded in 2001. Our optical network solutions address very diverse markets, ranging from subsea and long-haul, metro, and access. And our products have a global reach with tier 1 service providers, internet content providers, enterprise verticals. We have over 2,000 patents in a portfolio. And our commercial success is really in large part and continues to be due to the high degree of vertical integration that we have, which is really as a business, we are organized to leverage synergies of these multiple technical competencies that we feel are necessary to deliver high performance and reliable optical engines for different markets. So at the Optical Innovation Center, which is where our group is seating, we design and manufacture PICs in Sunnyvale, California. We also design and customize ASICs and drivers for our PICs, and design and build our own modules in Pennsylvania. So taking a system-centric approach, as Chris had mentioned earlier, right at the start of the design process allows us to understand the trade-offs and optimize the PIC performance in terms of how to deliver spectral efficiency, reach, and cost per bit. So this really comes together in terms of software and hardware. So how vertical integration really shows itself is that in order to optimize the performance of the engines, we need to also match analog and DSP ASICs. And we believe that a holistic co-design is really necessary to continue to drive innovation in our products. And this is really shown best in our most recent engines that demonstrate the power of holistic co-design that provide RF signal integrity to operate 800 gigabits per lambda on the indium phosphide PIC. And that product has been integrated with a high-density SIGI ASIC, and this allows us to achieve high modulation bandwidths in excess of 55 gigahertz, capable of 800 gigabits per second on the transmission, and then on the software and hardware co-design, we were using probabilistic constellation shapes, so we can do 64 QAM modulation format with Nyquist subcarriers. So if we have if we look at the evolution of our transceivers, at Infinera, we have pioneered the use of large-scale photonic integrations into the network since 2004, starting with a 10-channel, 10 gigabit module. And then as we move into coherent modules, we integrated 50 gigabit 10-channel modules and deploy those into the network. And these had TX that integrated over 600 functions on a monolithically integrated on an indium phosphide chip. So by continuing to increase the baud rate and the modulation formats, as Chris showed earlier, to achieve these larger pipes, the density of the integration of our transceivers really increased. In 2016, we demonstrated a 1.2 terabit module with a 200 gigabit per lambda PIC, and then went on to demonstrate 2.4 terabits with 600 gigabit PICs in 2019. And then most recently, our latest optical engine, which is 1.6 terabits. And these are 2-channel PICs, which for the first time integrated all the transmit and the receive optical functions onto a single indium phosphide chip. And each channel is running at 800 gigabits per second. So this these PICs are developed in a commercial fabrication line, and that fabrication line is now also accessible through a foundry capability. And so the same fabrication line that produces this leading edge commercial PICs was tailored to provide the foundry PDK that you'll hear from today. The development of the integration platform at Infinera is very similar to the development of electronic ICs. We start with the manufacturing capability, and once that capability is mapped out, we put in place fab processes with very tight CPKs and use end-of-line tests from the product lines to correlate performance and verify the design rules. So SPC metrics are used in all the product lines. Process capability is also used, and this is a measure of the repeatability and consistency of our manufacturing process. These capabilities are tracked and controlled to deliver high fabrication yields and meet performance metrics. So over 90% of the processes have CPKs in larger than 1.33. We've reported many times yields over 90% on our wafer fab production lines. So by developing integration platforms, we're also able to leverage learnings from these platforms, and they can transfer from one to the other. So from one product line all the way to the foundry capability. So what I'm showing here is an example of our 1.2 terabit process line, and here we see that the platform was first designed for C-band at 1550, center around 1550, and then the performance was transferred to L-band. These platform learnings, are leveraged throughout our entire processes, and you can see from the widely tunable laser threshold to the imbalance on the RX and the MZ VPIs that there's the performance is nearly identical on these two platforms, and we have leveraged that to utilize the performance of these devices to realize the external products or the external PICs that we have done in the foundry. So what I'm showing here is an example of an integrated mode-lock laser that uses photodetectors, widely tunable lasers, DFVs, and Mach senders. And then not only can we build those mode-lock lasers with the foundry capability, but we could also make arrays of these lasers. And This is actually pictures that we're taking from our recent publication in August, JQE. So beyond the process design rules, we also need to look at the scalability of the process. So improvements in the fabrication capability have reduced the density of killer defects, which enables the integration of PICs with larger and larger complexity and a number of functions. This is really important as, you know, if you think of a PIC yield, the yield is not just determined by meeting the performance of a specific channel metric, but it also needs to perform across all the different channels. So in this extreme example, we've shown in the lab a 40 channel transmitter PIC. This PIC has over 17 optical functions. And what that means is this is a coherent transmitter with IQ modulators, so 80 Mach senders. That means 160 Mach senders, power combiners, 40 DFB lasers that are targeted within a 20 gigahertz grid. That really demonstrates the precision of our wavelength targeting and manufacturing capability. And so, and to demonstrate, you know, the performance on the channels, I'm showing this QPSK constellation, and you can clearly see that the TE and the TM constellations for all 40 channels. So this is a 2.2 terabit capability 40 channel transmitter that's been all monolithically integrated in indium phosphide. So let me now highlight the components of the PDK and in the capability of the integration platform. So we offer lasers that are fully optimized in the platform. These components are all centered at 1550 nanometers. The DFB lasers can run CW or directly modulated. And then we also have in the kit DC and RF photodetectors. The kit the first release was at least operating at 10 gigahertz, followed by a second release, which has a capability of 20 to 25 gigahertz. We offer on-chip amplification, power and phase adjusters, and 10-channel AWG. And all of this is integrated in a low-loss optical integration platform. And what you see here is a micrograph of the chip of the wafer payload from one of our MPW runs. So we use, as I mentioned before, a system-centric approach to design all these components. So these are components that are compatible with off-the-shelf electronics and assembly requirements. They're also really intended to operate as best in class. So no, they stand out in well when compared with standalone components. So this particular laser is a widely tunable laser that came from a verification chip that was embedded into the MPW, and the line width is 200 kilohertz. It's compatible with standalone widely tunable lasers. We've also collaborated with external groups to test some of our components, and I'm showing here the RIN characterization from an integrated DFB laser, and the comparison here is made between a commercially available off-the-shelf DFB that is typically used on RF photonics and the Infinera laser. So the commercial line also provides a wealth of statistical data to build compact models. Eugene will be describing that after my talk. To enable this turnkey capability, we partner with InP Photonics, and that really helped us to chart a path for allowing users to prototype and move on to commercialization very quickly. So we developed the infrastructure to maintain the foundry line in our commercial fab and to use design automation to perform simulations and pick layouts. We've generated data to build compact models derived from the foundry that are not just based on our foundry runs, but also on statistical distributions from our commercial lines. Interoperability is also really important between these tools, and that was part of the joint collaboration that we had with InPhotonics. This really reduces the learning cycles. Eugene will talk about the netlist export capability today, which allows us to take the simulated PIC schematics and readily bring them into a layout environment, in this case as Cadence, and allows us then to quickly move from simulation to layout to fabrication and to delivery of the PICs. So I'd like to thank you for listening to the Foundry capability, and really look forward to working with you in the future.
Yes, thank you, Gloria, and thank you for that introduction to your indium phosphide foundry. And so now I'd like to introduce Eugene Sokolov, our photonics application engineer at VPIphotonics, and he's going to take you through the VPI toolkit Infinera PDK and show you a live demonstration of that using VPIphotonics design suite.
Thank you, Chris, for the introduction, and thank you, Gloria, for presenting these amazing results Infinera achieved. And hello everyone again. My name is Eugene Sokolov. I am a senior application engineer with VPIphotonics. And so today I'm going to discuss and show actually how VPI Toolkit PDK Infinera could help with the design process for Infinera customers. So some of you might be curious what VPIphotonics does and who we are. So we have been developing photonic design automation software for over 20 years now. And we have several offices and local representatives worldwide. I'm personally joining this webinar from the East Coast, from Greater Boston area. And we have very diverse range of customers, as among corporations, as well as from universities and research institutes. And we offer multiple software tools covering different applications and levels of abstraction. And you can see here a few examples on the right. So we start from waveguide and fiber design, going up to photonic integrated circuits and systems, and all the way up to networks. So we also share the knowledge we gathered over these years and take active part in several forward-looking research projects. So here's our product portfolio. As I mentioned, there are several different tools and extensions to them at different levels of abstraction. And yeah, you are most welcome to visit our website or contact us directly and study more about them. But for this particular webinar, we are going to focus on these tools: VPI component maker photonic circuits and the extension to it, providing the library of the building blocks for Infinera indium phosphide foundry PDK. At this level, one would have access to more physical presentation and more physical models of the integrated photonics components, while another tool, VPI transmission maker optical system, will focus on the entire optical systems, and you'll see the difference in a minute when I will be showing the demo. And but what is important, all three could work perfectly well together because they share the same user interface called VPI Design Suite. So now if we talk about integrated photonics design, and the main challenge with it is that we may have very diverse set of the basic photonics building blocks. Some of the models should be really advanced in order to capture all the effects. And there are other challenges too. So we need to deal both with electrical and optical signals. Our signal propagation should be bidirectional, so that we can account for back reflections in our integrated photonics, or counter-propagating signals interaction, and so on. So in order to address these and other challenges, we created the product called VPI Component Maker Photonic Circuits. And it can be used for, a really diverse range of applications. And as an example, we can see here tunable hybrid 3.5 silicon laser. Also important, it's also important that one can not only design and study alternatives of your designs and your solutions, but also do design optimization of these devices and circuits to investigate fabrication tolerances and perform sensitivity analysis. As was already mentioned today, one of the main trends and desires of the integrated photonics industry is to simplify access to design and manufacturing of PICs. To lower the cost, and it could be achieved by increasing design predictability and enabling very easy scalable design of highly integrated circuits, and surely speeding up the design cycle and reducing time to market. So following the paved path of the electronic IC designs, the foundry-specific process design kits are widely introduced to address these needs. So what is the PDK, right? In the first place, it is a list of optimized and predictable components which foundry could fabricate. So further, PDK contain corresponding compact models, and these models are fast, analytical, or behavioral models, which capture the actual behavior of the devices fabricated on the foundry. So simulation models require the parameters to be set, and this information is usually delivered by performing device, so physics-driven simulation, and by test and measurements. And the models themselves are already implemented in some circuit-level simulation tool. And so yeah, we propose a few tools which fit in this ecosystem. But what is most important, that this ecosystem proposes high interoperability of different tools. So what does it mean? For example, you have a circuit of your schematic, and could be quite easily converted into multiple layout tools, your favorite one, or just a netlist, as we will see in the future. And further, your circuit simulation could be combined with system or electrical simulation quite seamlessly. And depending on the task, all of these interfaces could be really important. Switching to how this ecosystem works, in particular case of Infinera PDK, we should note that Infinera Foundry does a tremendous job simplifying their customers' life. And Infinera accurately performs testing and measurements of their devices, and we use this information to characterize PDK compact models. So further, in this workflow, the users could not care about their PICs layout. Infinera takes care of that as well. And passing your abstract design idea after simulation would be as easy as sending netlist, which is automatically generated from your schematic. So to create such a dedicated library of building blocks for PDK, we have been working with Infinera, and here we can see the list of building blocks we currently support. So it includes as well as passive and tunable components and more sophisticated active devices such as modulators and lasers. So we use our built-in system-level models and tune them accurately, and depending on the nature of the components, different methods and simulations models could be employed. It is important to mention here that using the measured data is really measured and experimental data is really essential because we have more trust for more complex designs afterwards. And one can also extend the library with their custom co-simulation models. Now, let me give a few examples of how we characterize the simulation models. In a very simple case, the measured characteristics could be read pretty much directly. For example, passive devices are completely characterized with their scattering matrices. And as in case of this arrayed waveguide grating, which is commonly used to multiplex or demultiplex optical signals at different frequencies, we can just read the scattering matrix in some specific format. In other cases, the measured data could be processed before it is applied to optical signals in the simulation. And as an example, we can measure the response of the RF photodiode and approximate it with analytical low-pass filter. And the parameters of this low-pass filter are calculated quite easily by simple fitting procedure of actual experimental data. In both cases, the models are pretty straightforward and use foundry data almost directly. In other cases, more advanced components, such as Mach-Zehnder modulator, require more flexible simulation models. Sometimes these models are rather straightforward, and as in this case, they could be characterized with very few parameters which are easy to measure. In case of modulator, this could be VPI characteristic, extinction ratio, electro-optical amplitude response, and so on. And for example, this plot here shows the bias sweep representing VPI measurements of the modulator. And as we can see, this approach delivers pretty high accuracy. You know, we can compare the measured and simulated data, and it's really close. Unfortunately, direct measurements or calculation of model parameters is not always possible. And even in case of relatively simple rate equation model based on a small signal approximation we used for simulating DFB laser provided by Infinera, it is really hard to measure directly some of the characteristics, such as alpha factor, damping time, chip parameters, and so on. In such cases, we use more sophisticated procedures of the parameters extraction. So we use some optimization routines to extract the parameters from experimental data. And this allows to account for more physical effects, such as realistic amplitude and frequency modulation responses, dynamic adiabatic chirp, and so on. So on the plots here, we can compare a lie curve for the DFB laser diode, small signal amplitude response, and relative intensity noise spectra. And we can compare the measured and simulated results. And again, even with more complicated procedures, the simulation gives us sufficient accuracy. Shifting gears, let's see how all this works together in a live demo for 16QAM system based on Infinera PDK building blocks. And for this purpose, I'm going to switch to VPI design suite. So to start with, let me introduce the VPI design suite interface and the main elements that we will be talking about in the next few minutes. So a VPI design suite provides a dedicated visual photonic design environment. And this allows you to create an abstract representation of your system or circuit, which we usually call a schematic, and run the corresponding simulation without any programming knowledge, right? So it's very easy. Any schematic consists of interconnected building blocks, usually representing different devices. And on the left here, we can see the navigation bar where one can access a library with numerous modules, and for example, providing the models for laser sections or for the integrated passive components. So we use these models, these general purpose models, to create corresponding library of the Infinera PDK building blocks. And this library is also provided as an extension or toolkit, and it can perfectly work together with all general purpose components stored in this library. So there's also a vast library of demonstrations which are organized by different products. So once again, different products share the same user interface. And also they're organized by different folders according to the applications. So we can see some applications for the lasers and SOAs, for passive circuits, and so on. On top of that, we have demonstrations associated with a specific PDK. So this could be very easy, for example, just showing list of components or doing some characterization of individual components, or actual application examples. And one of them is actually open right now, and we're going to discuss in a moment. So at the top of the interface, we have a ribbon. And at this ribbon, we have multiple commands which are required to work with the current schematic and the simulation. In the simplest case, this would be just running and terminating the simulation. However, the central part of our workspace is a schematic. And it represents your system by connecting the models. And in addition, each design package could have individual associated resources here on the bottom. It's just scratching the surface of the interface. And now let me move to the example itself, okay? So this is an example of 16 QAM signal propagation over 10 kilometer fiber. And I'm not going dive deep into the principles of quadrature amplitude modulation or QAM format. Importantly, that this system contains the typical parts of any optical link, right? So it has transmitter, it has the link itself, usually represented by a fiber, and it has a receiver with some signal processing, okay? So if we have a look at the transmitter, we can distinguish electrical and optical part, and while electrical part is represented by the general purpose modules emulating electronic components, the optical part consists of Infinera PDK building blocks. So let us have a little closer look at them. And so here we have 2 bits sequences driving dual parallel Mach-Zehnder modulator. So it's basically 2 Mach-Zehnder modulators, which are standard Infinera building blocks embedded into a main Mach-Zehnder structure. The continual wave emission of the Infinera TFP laser is modulated by these modulators, and since there is a phase shift in one of the arms, we can form in-phase and quadrature data streams. So we can open the parameters of the one of the modulators. And once again, since this modulator is part of Infinera PDK building block library, the model is already pre-adjusted so that it reproduces the functionality of the real device. And because of that, there are very little parameters to control and to set up. And this is an advantage, right? Because it makes it very easy to use such components. So for example, we can control here the heating power, emulating the phase shift change in the thermal phase shifters. We can adjust extinction ratio, so simulating some fabrication tolerances, for example, and we can switch on and off some of the effects. So after some auxiliary modules here, we pass our signal to the fiber, and which is further detected in the receiver by superimposing the signal with the local oscillator emission in the integrated 90 degrees hybrid. And further, the signal is detected in the photodiodes. And there is also some signal processing tools, which we will discuss a little later. Importantly, the same as in the transmitter, the optical part of the receiver is also represented by the integrated Infinera PDK building blocks. Okay, let me run the simulation now. Okay, I'll just show you very briefly the simulation. So currently we switched off pretty much all the effects. So we have very ideal extinction ratio for the modulator. We switched off the fiber and all associated results. So the simulation doesn't take long. And since all impairments are dismissed, our constellation diagram is detected by the receiver is pretty much ideal. Now let me switch on some of the effects, and yeah, to save a little of time, let me do them all at once. So I switched on fiber and corresponding dispersion and probably some nonlinear effects. If we have some, we can return back a realistic extinction ratio of the modulator, and we can also switch on the S to1 response of the modulator. And let's see the simulation results in this case. So actually the results are shown in the VPIphotonics analyzer tool. So it's a dedicated tool for the analysis and visualization of the optical and the electrical signals. And now we can see that, okay, surely switching on the impairments in fiber and in our modulators will affect our constellation diagram significantly. Going a little more, we can introduce phase noise. Because I used a little trick, I considered my local oscillator and the transmitter laser to be completely coherent. And we can see that once this phase noise is introduced, we can hardly distinguish our symbols. How to fix that? We need to introduce some DSP blocks. In our case, we just switch them on. And by the way, I'm using this macros as just setting the parameters. No magic is going on here. So once we activated this DSP digital signal processing building blocks here, our algorithms, some algorithms for phase recovery are applied, and we can see how these algorithms can improve our constellation diagram, and our symbols could be distinguished pretty easily again. So please notice again that all the components here, so for example, these DSP components are from the optical systems tool, while these are from Infinera PDK building blocks library. And this shows very high interoperability of different tools and components. So it was a very simple example of the analysis which optical designer could perform. So once he's happy with that, he can export the schematic into the netlist and pass it to Infinera. And for that, we have dedicated script here. So let me save this pass and finish the result. So yeah, we can obtain this netlist, which could be further passed to Infinera. Even more, we can import the netlist, so we can go the other way around. And for example, in foundry, if Infinera did some changes and we want to check if the circuit still operates properly, we can automatically generate the schematic from the netlist. And surely it will not include any general purpose components such as fibers or digital signal processing tools, but only the components which are related to the PDK Infinera building blocks. But a regular workflow would be and providing the generated netlist to Infinera for subsequent import to layout tools, and ultimately taping out the chip. And this concludes my part of the presentation. So sorry for taking a little longer. And I have my pleasure to hand over to our partners from Infinera now. Thank you for your attention.
Thank you, Eugene. And we're going to switch over now to Yuchun, who will show you now once the netlist is exported and delivered to Infinera, what the workflow looks like from his point of view.
All right, thanks again, Chris. So as Eugene just introduced, I'm going to show how we would be able to import the spice-like netlist file containing the components location, rotation, and the ports connection information into the layout to be used internally in Infinera. In this case, is Cadence Virtuoso for the foundry service. And specifically, we will use the exact 16-QAM circuit that Eugene just showed as an example for the lab demo. First, we copy the exact netlist file of the 16-QAM circuit generated from the VPIphotonics into Cadence server. The import process can be done through a simple click, and the schematic will be generated directly in the library manager. As we can see here, the spice file has been loaded automatically, and the schematic can be opened in the view window over here. Next, by implementing our internal developed scripts through hitting a shortcut key, the location, rotation of each component will be updated according to the parameters provided in the netlist file. As we can see here from the updated schematic in Cadence Virtuoso, the circuits are all like the user constructed in the VPIphotonics component maker, where the key circuit construction information can be imparted to the Infinera team seamlessly. So as a turnkey foundry, Infinera does provide a full suite of standardized devices that users only need to provide the PIC schematics without the need to design their own devices, since Infinera already has fully optimized IP blocks ready to use already. And we will take over from the finalized schematics all the way to produce a final functioning chip. The EPDA Flow shown here illustrates the whole ecosystems we've been using so far to fabricate the chips for the foundry users. As mentioned earlier, the blocks highlighted in the blue are the parts that we've covered today so far, and through knowledge generation from VPIphotonics, we are able to import the schematics into Cadence to do LVS and DRC, and all the way to the GDS file generations for mask orderings. And during and after the fabrication, through testing on the integrated test device structures on each die from the MPW foundry run, we have the capability to make sure the successful realization of all the active and passive devices and optical links requested by the customers. So here we just like to present some actual micrographs of an actual chip where bonded to the carrier, where you can see the IC metal traces across the whole chip clearly, and how the wires are bonded to the PC pads and fan out. Two zoomed in areas show both a ceramic pedestal on the top of the chip for RF wire shortenings and impedance matching, as well as the thermistor incorporated on the COC for characterizations using TECs. We also have some alignment features on each die using on-chip lasers with outputs to the facets directly. The users will finally get a similar packaged chip like this if requested. And with specialized and customized probe card, one can begin automatic chip characterizations or to actually use the chip. Again, the performance of the components and the PIC is quite competitive with the state-of-the-art of the Indian phosphide foundries around the world. And we currently provide a full set of requisite components for both TX and RX applications. So far, we've introduced how Infinera's EPDA and the foundry process flow look like, and in terms of the cycle time, as long as the PIC design has been verified by both foundry customers who are, in the meantime, VPIphotonics customers, in this case, and the Infinera team, from PIC fabrication all the way to COC delivery is usually within 4 months. And starting from 2019, we have already successfully finished our first MPW foundry run and delivered the chips to a few foundry customers already. So if you have any questions, please feel free to contact us through the following emails, or contact me or Gloria directly through these email addresses, or in terms of the circuit simulations, you're welcome to send questions to Chris or Eugene too.
Great, thank you, Chun. And I think that's all the time we have today. So I just like to thank everybody, and please reach out to us if you have further questions. Our emails are below, and you can visit the website.
Thanks, Chris. Thank you guys all for participating. Thank you to our attendees for joining us. So I hope you guys all enjoyed today's presentation. Thank you guys so much for attending, and we'll see you again at the next one.